Hello again, everybody, and welcome back. This video segment is going to be pretty short. It's going to be simply on this one topic of springs and Hooke's law. Now, what you see below at the bottom, that equation, is Hooke's law, and it involves finding what the force is that a spring applies. Many springs can be either pushed or pulled, but depending on how much you squeeze it, how much you compress it, that will determine what the force is that the spring applies. So a spring at rest, we would say that has its equilibrium length. All right, so let me just go ahead and draw, I'll draw a spring right here at the very bottom. Okay, that's a spring, and that is its equilibrium length. Let me kind of erase that little first part right there. All right, so it's normally that length. If we stretch it out, that displacement right there, that delta x from here to here, the force that the spring will apply, F sub s right here, is a combination of two things. It is that displacement, that delta x, times a value that we call k. K. Now, I'll describe that in just a second, but if we stretch it out towards the outside, all right, if we stretch out the spring lengthwise, the pull that it's going to apply is going to be back in towards the center, right? So the force that it's going to apply is going to be back to the original equilibrium length. Similarly, if we squeeze down a spring so it's a lot shorter, like that, well, here's our new here's our new displacement right here. They look to be about the same, just in different directions. So this one right here has been squished down by about that length, and it's going to apply back a force. So we squeeze it down. Oops, that's the wrong color. Use blue. We squeeze it down like that, and so if we compress it inwards, the spring itself is going to apply an outward force. So springs always apply a force in the opposite direction that you compress them. All right, well, what is the force? Well, it's a function of that amount of displacement, and the force that a spring applies is the displacement times what's called the spring constant K. The spring constant K. It's a value of how stiff the spring is. All right, it's really just a multiplier. Well, it does have some units. But the stiffer the spring, the higher the K constant. All right, the K constant is measured in, let me just give you a hypothetical value, say 10 newtons per meter. Newtons per meter is the unit that the spring constant has. And that means if you displace that spring 1 meter, the spring will feed back 10 newtons worth of force. Whether you squeeze it inwards or you pull it outwards, whether it's a pull or a push, it doesn't matter. If you push it in, the spring will push outwards oppositely. If you pull it out, the spring will pull back in towards the equilibrium length. But the amount that you stretch it, that is that displacement right there, times the spring constant K, is going to give you that force. So let's just say the force of a spring we want to find, and so the spring has a spring constant of, we'll say, like we did up above, 10 newtons per meter. So this is our spring constant, 10 newtons per meter, and we multiply it by x, or that is our displacement, which is measured in meters. So and we only displace it maybe a half a meter. Okay, we stretch it or compress it 0.5 meters. What happens right there? Well, the reason that the spring constant has units is because it causes these units to cancel out. So the meter goes away, and you're left simply with a value in newtons, which is what force is. So 10 times 0.5, that'll be 5.0 newtons. That would be the force that the spring is applying. Okay, so we're just going to introduce it right now. We're going to look at this at more length in future chapters, but this is the idea of Hooke's law. Is the amount that you compress a spring or extend it is going to result in a greater or lesser force feedback by the spring. If you compress it a little bit, it'll feed back with a little bit of force. If you compress it a lot, it'll feed back with a lot of force. A little problem right here, a little example. This will be pretty easy. It'll just be an application of the spring constant. So right here on the far left is this bulldozer. It's attached to a spring, which is attached to the wall. All right. The bulldozer is going to apply a force to the spring, and it's going to stretch it out. It wasn't a very well drawn arrow, was it? It's going to stretch it out like so. And of course the wall is going to pull back on the spring because the wall isn't going to go anywhere. So the bulldozer, I guess it's a little toy bulldozer, it stretches this spring 0.45 meters. So that value right there, our displacement, is 0.45 meters. That's the amount that the spring is stretched. Okay? And it has a spring constant, the K, equals, we're told, 1,300 newtons per meter. That's a lot more than the spring constant that I just made up a minute ago, right? 1,300 newtons per meter is the spring constant. And we want to find the magnitude and direction of the force the spring exerts on the wall and the bulldozer. Okay? So the wall is pulling outwards that way. The bulldozer is pulling out that way. So what direction? First of all, let's just kind of conceptually think about this. If the bulldozer is pulling out, as is the wall way back over here, what direction does the spring have to be pulling? The spring has to be pulling that direction on the bulldozer and that direction on the wall, right? So it pulls on the wall in the positive direction. It pulls on the bulldozer in the negative direction. We kind of established the direction first. Now let's just find the magnitude of that force, the spring constant force. The force that the spring is applying is simply what? Hooke's law, right? Kx. The spring constant, 1,300 newtons per meter, times how many meters? 0.45 meters. Okay, and of course our meters cancel out, and we're left with a value in simply newtons. So what is 1,300 times 0.45? I get 585. That's the magnitude of the force that the spring is applying, right there. If we stretch the spring less, it would feed back with less force. If we stretch the spring more, it would feed back with more force. But for this displacement, 0.45 meters, that's the force that the spring is feeding back. So apparently the bulldozer can withstand that because it's stretching the spring to that length right there. Okay, that's a good application of Hooke's law, which we're going to look into, like I said, more in future chapters, but just wanted to introduce this to you so you have the idea of how to find the the force created by a spring. All right, thanks for following along. Make sure you contact me and let me know if you have any questions.